We will now discuss multicollinearity, a significant issue that can arise in multiple regression analysis. Multicollinearity is a phenomenon in regression analysis where two or more independent variables are highly correlated with each other. This high degree of correlation can make it difficult to determine the individual effects of each independent variable on the dependent variable. Multicollinearity can arise for various reasons, such as when two or more independent variables measure similar or overlapping concepts, or when they are computed from the same underlying data. Multicollinearity can also arise when there's a small sample size, leading to imprecise estimates of the correlation between independent variables. The primary consequence of multicollinearity is that it increases the variances and standard errors of the regression estimates of coefficients and the predicted values of the dependent variable. Consequently, this can lead to erroneous results in the hypothesis test for the individual independent variables. When multicollinearity is present, the estimated regression coefficients may become unstable or inaccurate, rendering them unreliable predictors of the true underlying relationship between the independent variables and the dependent variable. In some cases, multicollinearity can even lead to paradoxical or counterintuitive results, such as an apparent reversal in the size of one or more independent variables. An independent variable found to be non-significant in a regression analysis may, in fact, have a strong relationship with the dependent variable. Conversely, an independent variable previously deemed important could be found to be insignificant. Even if the overall R-square of a regression model is large, it is possible that none of the individual coefficients are statistically significant. Furthermore, significant changes in the regression coefficients can occur after a variable is removed from the model. In the worst case, the presence of multicollinearity can render the analysis outcomes unusable for interpreting the relationship between the dependent variable and the independent variables. Given these potential consequences, it is crucial for us to identify and address multicollinearity in our analysis. Several approaches can be used to measure multicollinearity. One method involves observing the correlation among independent variables. High correlation between two predictor variables, indicated by correlation coefficients near +1 or -1, may suggest the presence of multicollinearity. As a common rule of thumb, multicollinearity could be a potential problem if the absolute value of the sample correlation coefficients surpasses 0.7 between any pair of independent variables. Some researchers may opt for a higher threshold, such as 0.85, depending on the specific requirement of the regression models. In order to ascertain whether multicollinearity is a significant concern in the heating cost case, we construct a correlation matrix. This matrix displays the correlation coefficients for all variable pairs. As depicted in this correlation table, the highlighted area shows the correlations among the independent variables in the heating cost case. Given that no correlation coefficient surpasses 0.7, we can infer that multicollinearity is not a significant issue in this instance. The second approach to measure multicollinearity involves the use of the variance inflation factor, VIF, which quantifies the extent to which the variance of the estimated regression coefficient is amplified due to multicollinearity. A VIF value of 1 suggests no multicollinearity, while a value greater than 1 implies its presence. Defined by 1 over 1 minus adjusted R-square, the VIF is proportional to the variance of the regression coefficients. Generally, a VIF value exceeding 5 or 10 is viewed as indicative of problematic multicollinearity. Certain researchers assert that a VIF greater than 10 is unsatisfactory, suggesting that the independent variable should be eliminated from the analysis. Using software like SPSS, the coefficient table will also comprise the tolerance and VIF values for each independent variable. In the heating cost case, as demonstrated in this table, all VIF values are below 2, indicating that multicollinearity does not pose a significant concern for the heating cost regression model. We will now discuss another set of multicollinearity measures, the condition index and the variance proportion. Both measures are available in the SPSS collinearity diagnostics component, which can be selected within the regression model. Eigenvalues measure the amount of variation in the data explained by each eigenvector of the correlation matrix. In contrast, the condition index measures the overall degrees of multicollinearity in the data. The largest condition index is termed the condition number. A condition number between 10 and 30 indicates the presence of multicollinearity, and a value larger than 30 signifies strong multicollinearity. Each explanatory variable has variance decomposition proportions corresponding to each condition index. The total sum of the variance decomposition proportions for a single explanatory variable equals 1. If two or more variance decomposition proportions corresponding to condition indices higher than 10 to 30 exceed 80% to 90%, multicollinearity is determined to be present among the explanatory variables corresponding to those exceeding variance decomposition proportions. In the table obtained from SPSS, most conditional indices falls below 10, with the exception of the fourth variable, age. However, the corresponding variance proportions are 0.61, 0.26, and 0.52, all of which fall below 0.8. Thus, while multicollinearity is a concern, it is not severe. In summary, we have discussed three major approaches to measure multicollinearity. Each approach offers a unique way to gauge the extent of multicollinearity in a regression model. It is crucial to employ multiple measures to assess the presence and severity of multicollinearity, which will enable informed decisions about how to address it in the analysis. To address the issue of multicollinearity, we can do the following. First, we may want to check to see if one of the independent variables is a duplicate or redundant. Duplicate and redundant variables should be removed from the dataset before running a regression analysis, as they can affect the accuracy of the model and lead to biased results. Second, be careful when creating dummy variables from categorical variables. When creating dummy variables, it is important to avoid creating redundant variables, as this can lead to multicollinearity and affect the interpretability of the model. Third, aggregate similar variables, such as adding them together. If multiple independent variables are measuring the same underlying contract, it may be appropriate to aggregate them into a single variable to reduce the number of variables in the model and improve the interpretability of the result. Fourth, increase sample size. Increasing the sample size can improve the accuracy of the regression model by reducing the standard error of the coefficients and increasing the statistical power of the analysis. A larger sample size can also help to reduce the impact of the outliers and improve the generalizability of the result. Fifth, remove some of the highly correlated independent variables. If two or more independent variables are highly correlated, it is important to remove one of them to reduce multicollinearity and improve the accuracy of the regression model.